Hello students, today's topic from inorganic chemistry, coordination compounds. So inorganic compounds are classified into three types. They are simple salts, double salts and coordination compounds or complex compound. Simple salt is one which is made up of one basic radical and one acid radical. For example, potassium chloride. It contains K plus as basic radical and Cl minus as acid radical. So next about double salts. Double salts. These are composed of two simple salts. Example for double salt, potash alum. Potash alum. K2SO4, Al2SO4 thrice and 24 molecules of water. More salt, ferrous ammonium sulfate. It's a combination of two simple salts like ferrous sulfate, ammonium sulfate. So one more about carnallite. Carnallite is an important mineral of chlorine. Carnallite. KCl dot MgCl2 dot 6H2O. Say. So combination of two simple salts. They are called as double salt. And these double salt, they are stable only in solid state. When they dissolve in water, they dissociate to give its constituent ions. Next about complex compounds or coordination compounds. Complex compounds. So these are the compounds in which central metal atom or metal ion is bonded with definite number of anions or neutral molecules called ligands. And they are stable in both solid form, solid state, as well as liquid state. Example for complex compound, potassium ferrocyanide, potassium ferrocyanide, K4FeCN6, potassium ferrocyanide, cuprammonium sulfate, Cu, NH3, 4 times SO4, cuprammonium sulfate. So these are the different types of inorganic compound, Next about complex ion. Complex ion is a charged species where central metal ion or metal atom is bonded with definite number of ligands. Such electrically charged part is called as complex ion. Complex ion. Now for example, in the formation of ferrocyanide ion, ferrous ion Fe plus 2 combines with 6 cyanide ligands that gives ferrocyanide ion. Similarly, cupric ion Cu plus 2 combines with neutral ligand amine that gives cuprammonium ion. Okay. Now based on the type of complex ion, there are different types of complex. Okay. Cationic complex. Here complex ion is cation. Example for complex cation, cuprammonium ion, and example for cationic complex is cuprammonium sulfate. Cu NH3 4 times SO4, cuprammonium sulfate. Next about anionic complex. Here complex anion, complex This complex compound contains complex anion. Such type of complex called as anionic complex. Example, potassium ferrocyanide K4 Fe CN6. Now, in potassium ferrocyanide, say ferrocyanide ion is a complex ion and it contains negative charge. Therefore, it is an example for anionic complex. Next one, neutral complex. Neutral complex. Example for neutral complex, nickel tetracarbonyl. Nickel tetracarbonyl is an example for neutral complex. Next, about the term ligands. So, what are called ligands? Negative ions or neutral molecules capable of donating at least one lone pair of electrons to the central metal atom or metal ion. During the formation of complex compound, they are called as ligands. Ligand. So, based on the number of donor atom, ligating atom, there are different types of ligands. First one, monodentate ligands. Monodentate ligand. So, number of donor atom, 1. One donor atom. Okay. Ligating atom is 1. Denticity is 1. Some example for monodentate, aqua, water, H2O. Ammonia as a ligand is called as amine. Then negative ligands like Cl minus, Cn minus. These are example for monodentate ligands. Next, about bidentate ligands or didentate. Bidentate ligands, or they are also called as didentate. There are 2 donor atoms, 2 ligating atom. Denticity is 2. Example for bidentate, ethylene diamine is also called as EN, ethylene diamine. CH2, NH2, CH2, NH2, ethylene diamine. This is an example of neutral bidentate. Now, negative bidentate, oxalato ion, COO minus, COO minus. One more example for negative bidentate ligand, DMG, dimethyl glyoxide, DMG, dimethyl glyoxide. The structure, when you see the structure, it looks like neutral, but it carries negative charge. Now, dimethyl glyoxide. We'll write like this. Dimethyl glyoxide. So, it loses hydrogen, as a result it acquires negative charge. Therefore, it's an example for bidentate negative ligands. Now, next about tridentate ligands, tridentate. There are 3 donor atoms, ligating atoms 3, denticity is 3. Okay. Example for tridentate, diethylene triamine, CH2, NH, CH2. This contains NH2 group. So, these 3 nitrogen atoms act as a donor atom. Say. As a result, per ligand, 3 coordinate bond is formed. Per ligand, 3 coordinate bonds are formed. This is an example for tridentate ligand. Similarly, we can go for one more example, terry, 2 dash, 2 double dash, terpyridine. Okay. It's also called as terry. Now, Next one about the tetradentate ligand. Tetradentate ligand. In tetradentate ligand, there are 4 ligating atoms. Denticity is 4. Denticity is 4. Donor atoms are 4. So per ligand, it forms 4 coordinate bond. Tetradentate. Tetradentate ligands. Triene. Example for tetradentate triene. Triethylene diamine. Okay. Triethylene tetramine. Triethylene tetramine. Triene. Triethylene tetramine. Now, look here. There are 3 ethylene group. CH2. CH2. 4 amino group. Now, there are 4 donor atoms. Nitrogen, it acts as a donor atom. Triethylene tetramine. See, is an example for tetradentate. Similar, all these comes under polydentate. Similarly, we can go for pentadentate ligand. Pentadentate ligand. So, example for pentadentate, there are 5 donor atom. Pentadentate. Pentadentate. Okay. Example for pentadentate, ethylene diamine triacetate ion. Ethylene diamine triacetate ion. Now, look here. CH2, ethylene group, diamine, NH2, and these 2 hydrogen atom is replaced by acetate ion. Here, NH2, 1 hydrogen atom is replaced by acetate ion. Acetate ion. Now, in this, 2 nitrogen atoms and 3 oxygen atoms, it acts as donor atoms. So, total number of donor atoms are 5. So, it is an example for pentadentate. Similarly, one more, hexadentate ligand. Hexadentate. There are 6 donor atoms. Per ligand, it forms 6 coordinate bond. Per ligand, it forms 6 coordinate bond. Now, example for hexadentate ligand. Hexadentate ligand. Hexadentate ligand. EDTA. Ethylene diamine tetraacetate. Now, this is ethylene diamine triacetate. This compound is ethylene diamine tetraacetate. So, we can write the structure like this. CH2, N, CH2, COO minus, CH2, COO minus, N, CH2, COO minus, CH2, COO minus. Here 2 nitrogen atoms and 4 oxygen atoms, it acts as donor atoms. So, it is an example for hexadentate ligand. Example for hexadentate ligand is ethylene diamine tetraacetate ion. Now, next about ambidentate. So, these are monodentate ligand. Per ligand there are 2 donor atoms, but at a time only 1 donor atom donates a pair of electrons. Such type of ligands are called as ambidentate ligands. Ambidentate. Example, NO2 group. If you take NO2 group, in NO2 group, nitrogen and oxygen is the donor atom. So, if you write like this, ONO, oxygen the donor atom. If you write NO2, nitrogen the donor atom. Therefore, it is an example for ambidentate ligand. Similarly, one more example for ambidentate ligand, thiocyanide ion. This also contains two donor atoms, sulfur as well as nitrogen. So, it is an example for ambidentate ligand. And one more type of ligands are called as chelating ligand, chelating ligands, chelates. In chelating ligands, these are polydentate ligands, bidentate, tridentate, tetradentate, like that. And they form ring-like structure around the central metal atom or metal ion. Such kind of ligands are called as chelating ligands. Now, based on type of ligands, there are two more types of complex compound, homolyptic complex and heterolyptic complex. Now, what about homolyptic complex? Homolyptic. In homolyptic complex, the complex compound consists of only one type of ligand, identical ligand. For example, cuprammonium sulfate, or potassium ferrocyanide, Look here, this complex is made up of only one type of ligand, that is amine. Here, this complex is made up of only one type of ligand, that is cyanide. This is called homolyptic. Next one is heterolyptic complex. Heterolyptic complex. So these are the complex compound which contains the different ligands attached to the central metal atom or metal ion. For example, this complex compound contains amine as well as chlorido ligands. So central metal atom is bonded with two different ligands. Such kind of complex, two or more, but here only there are two different ligands, is an example for heterolyptic complex. So this classification is based on the types of ligands. Now, next about the term, the coordination number. Now, what is called coordination number? The coordination number is defined as the number of coordinate bonds formed around the central metal atom or metal ion in a complex compound. So, number of coordinate bond is called as coordination number. In the case of monodentate ligand, number of ligands, that is equals to number of coordinate bond, coordination number. Now, for example, in the case of monodentate, potassium ferrocyanide. See, there are 6 cyanide ligands. Each ligand contributes for a coordinate bond. Number of coordinate bond is 6. So coordination number is equal to 6. We'll take bidentate ligand, bidentate ligand. En stands for ethylene diamine. This is an example for bidentate. In bidentate, per ligand there are 2 coordinate bonds. So there are 3 bidentate ligand. Number of coordinate bonds equal to 6. Coordination number is equal to 6. So coordination number is defined as the number of coordinate bonds formed by the ligands around the central metal atom or metal ion. Then about the terms like coordination sphere and ionization sphere. If you take this compound, potassium ferrocyanide, when central metal atom is bonded with ligands, that part is written always inside the square bracket that represent coordination sphere. Any ion written outside the square bracket that represent ionization sphere. Now, this is ionization sphere. This one is coordination sphere, coordination sphere. The coordination sphere that indicates central metal atom or metal ion, about the nature of the ligand and about the coordination number. All this information is given by coordination sphere, coordination sphere. And these terms are important to identify which type of complex. For example, here simple ion is positive ion, complex 7 is negative ion. So, this is an example of negative complex. In this case, this example, simple ion is negative ion, chloride Cl minus. So, this part carries positive charge. So, it is an example for positive complex. So, this is about coordination sphere and the ionization sphere. Next, about types of coordination polyhedron. Coordination polyhedron. Coordination polyhedron. Now, it's about the coordination polyhedron that refers to the spatial arrangement of ligands around the central metal atom or metal ion that leads to definite give definite geometry of the compound. The polyhedrons are octahedral, square planar, tetrahedral. So, these are the common coordination polyhedron, common coordination polyhedron. Now, next, moving on to the calculation of oxidation number of central metal atom or metal ion. Now, oxidation number. Of central metal atom or metal ion. If ion is given, then you can calculate the oxidation state of the central metal ion or metal atom by considering charge present on the ligand. Now, and sum of the charge that is equals to charge on the ion. Now, for example, ferricyanide ion, Fe, Cn, 6 minus 3. Now, what is the oxidation state of ion? As the name indicates, ferri means it is plus 3. Now, how to calculate this? Let it be x plus. Cyanide is minus 1 into 6. This is equals to minus 3. X is equals to minus 6 minus 3. So, x is equals to minus 3 plus 6, that is equals to plus 3. If the complex is given, then sum of the oxidation state that is equals to 0. Now, if you take potassium ferrocyanide, in potassium ferrocyanide, K4, Fe, Cn, 6, K plus 4 positive charge. For this you have to calculate x. This is minus 1. Now, we'll go for oxidation state. Say, write like this, plus 1. Plus 1 into 4 plus x plus minus 1 into 6 equal to 0. So, this is 4 plus x minus 6 equal to 0. X value is equal to plus 2. As the name indicates, potassium ferrocyanide, ferrous, oxidation state is plus 2. Like this, you can calculate oxidation state of central metal atom or metal ion in a given complex. Next, about the term effective atomic number, EAN. Sedgwick proposed the effective atomic number, and according to this theory, during the formation of complex ion, central metal atom or metal ion continues to accept donated electrons from the ligand until total number of electrons around the central metal atom or metal ion becomes equal to atomic number of next higher noble gas atom. And most of the complex compound obeys EAN rule. How to calculate effective atomic number? EAN means effective atomic number. En is equal to Z minus X plus Y. Z minus X plus Y. Z is atomic number. X is oxidation state, number of electrons lost by the metal atom to form metal ion. Y is total number of electrons donated by the ligand. Each ligand donates 2 electrons. And also that depends on the nature of the ligand. Now, for example, we will take the first compound, zinc ammonium sulfate. Zinc ammonium sulfate. Effective atomic number of zinc. Effective atomic number of zinc, EAN. What the atomic number of zinc? 30. Here oxidation state of zinc is plus 2. Number of electron lost plus 2. It is also called as primary valency. Primary valency. Now, there are 4 amine ligands. Each amine ligand donates a pair of electron. 30 minus 2 plus 8. This is equals to 36. 36 is the atomic number of next noble gas called krypton. Now, one more example we can take. One more example. Nickel tetracarbonyl. Nickel tetracarbonyl. Nickel tetracarbonyl. En of nickel. En of nickel. It is a neutral complex where nickel is in atomic state, not in ionic state. Atomic number of nickel is 28. 28. Charge is 0 plus 2 into 4. 2 into 4. This is 28 plus 8. It is equals to 36. 36. Now, same we can take one more example. Potassium ferrocyanide. Potassium ferrocyanide. Same example we take. Potassium ferrocyanide. K4 FeCN6. K4 FeCN6. Here. En of iron, EAN, it is equals to atomic number of iron 26, oxidation state 2. Then there are 6 ligands. Each ligand donates 2 electrons, 2 into 6. 26 minus 2, 12. This is equals to 36. All these compounds obey EAN. Now, one more, cuprammonium sulfate. Cuprammonium sulfate. Cu NH3 4 times SO4. SO4. Now, about copper, En of copper. Atomic number of copper is 29. Copper is in plus 2 state. X value is 2. Then there are 4 ligands. Each ligand donates 2 electrons. So this is equals to 29 minus 2 plus 8. This is 35. Now this compound fails to obey En because 36 is the atomic number of next higher gas, higher noble gas, that is krypton. But here we got 35. So this is about calculation of EAN. Now, next about Werner's theory. Werner's theory. Okay. Alfred Werner is considered as the father of coordination compounds. Father of coordination compound. And he was awarded Nobel Prize for his work on coordination compound. So about the postulates of Werner's theory. Postulates. So according to Werner's theory, there are 2 types of valencies in complex compound. Primary valency and secondary valency, or primary linkage and secondary linkage. Primary valency, that refers to charge on the ion, and it is ionizable, variable, ionizable. Secondary valency, it is non-variable. Secondary valency, it is non-variable. Secondary valency is non-variable. Third one. Secondary valencies are arranged around the central metal atom or metal ion in order to give definite geometry. Fourth one. Primary valency is satisfied by negative ions whereas secondary valence is satisfied by negative ions or neutral molecules called ligands. Neutral molecules called ligands. Now, we'll take one example. Potassium ferrocyanide and potassium ferricyanide. K4, Fe, CN6, potassium ferrocyanide. And potassium ferricyanide, K3, Fe, CN6. Now, here, central metal ion is Fe plus 2. In this case, central metal ion is Fe plus 3. So, primary valency is plus 2. Here, primary valency is plus 3. Secondary valency 6. And here also secondary valency is fixed. See, secondary valency is fixed, but primary valency is variable. Okay. So, this is about Werner's theory, and according to this theory, there is clear distinction between primary valency or primary linkage and secondary linkage. Now, so after Werner's theory, next about the properties of cobalt amine complex. Properties of cobalt amine complex. Now, so this concept also very important one. When cobalt chloride COCl3, this reacts with ammonia, it forms different types of complex like CO NH3 6 times Cl3. Okay. Or we can write like this. Say, cobalt chloride, when it reacts with ammonia, that forms different types of complex. So, different types of complex, they are formed like this. CO, Cl3, 6 NH3. Formula of this complex is this one. Or CO, Cl3, 5 NH3, CO, Cl3, 4 NH3, CO, Cl3, 3 NH3. Now, by knowing the colligative property of these compounds, so colligative property or by molar conductivity, we can determine how many ions are present, or by treating with silver nitrate. Now, look here. In the first complex, this compound on treating with silver nitrate, 3 moles of silver chloride is precipitated. Number of ions formed, that is equals to 4. Number of ions formed, that is equals to 4. I'll write separately. Just look here. The first complex, CO, Cl3, 6 NH3. Okay. On treating with silver nitrate, AgNO3, that gives 3 moles of AgCl. Now, when it forms 3 moles of AgCl, okay, the number of ions, total number of ions, that is equals to 4. Number of ions equals to 4. Now I'll write the complex compound. CO, NH3, 6 times, and Cl3. Similarly, for the next complex, CO, Cl3, 5, NH3. Now, first I'll write the formula for the complex, CO, NH3 5 times, Cl and Cl2. This complex on treating with AgNO3 that gives 2 moles of AgCl. Is it correct? 2 moles of AgCl, because there are 2 simple ions, but total number of ions formed, that is equals to 3. Similarly, another one formula, COCl3 4NH3. This forms CO 4NH3 Cl2 and Cl, and this forms 1 mole of AgCl. Number of ions formed, that is equals to 2. Number of ions, that is equals to. The last one, COCl3 dot 3NH3. This forms complex like this. The formula of the complex. There is no simple ion, so no AgCl is formed. And it gives only 1. Okay. So this is about the property of cobalt complex, and this concept is asked in almost all competitive examination many times. So you have to remember just by knowing the formula or how to identify number of AgCl formed. For example, if they given the complex compound, cobalt compound on treating with ammonia, then followed by on treating with AgNO3, silver nitrate, if it gives 2 moles of AgCl, what is the formula for the complex compound? 2 moles of AgCl means there should be 2 simple ion, chloride ion, that reacts with AgNO3 to give 2 moles of AgCl. Then you can write the 2 simple ion, then remaining where cobalt forms an octahedral complex. Around cobalt, there should be 6 ligands. First preference is given for amine, it is a strong ligand. Then chloride ligand, that is a weak ligand. Therefore, we can write the formula like this. Okay. So this is about the property of cobalt complex. Next, quickly moving on to IUPAC nomenclature of coordination compound. IUPAC nomenclature of coordination compounds. IUPAC nomenclature. While naming the complex compound, first preference is given for cation, whether it is simple ion or complex ion. If complex ion is a cation, while naming the complex ion, you have to indicate the number of ligands, and first preference is given for name of the ligand. Name of the ligand is followed by name of the central metal atom or metal ion, and it is followed by the oxidation state. Then, while naming the ligand, if negative ligand ends with IDE, where E is replaced by O, it becomes IDO. Or in negative ligands, name of the ligand ends with ATE, E is replaced by O. Carbonate, it becomes carbonato. Oxalate, it becomes oxalato. Nitrate, nitrato. Chloride, chlorido. Cyanide, cyanido. This is about some of the negative ligands. Then, if there are more than one similar ligands are attached to the central metal atom or metal ion, the prefixes like di, tri, tetra are used. In the case of complex ligand means ligand, name of the ligand itself contains some of the prefix, like ethylene diamine, there is one prefix di. This kind of ligands are called as complex ligand. While naming the complex ligand, prefixes like bis, tris, tetrakis, pentakis is used. Bis refers to 2 complex ligand. Tris 3, tetrakis 4, pentakis it is 5. And if complex compound contains 2 or more different ligands, while naming the ligands, alphabetical order of the ligand should be followed. Then about the cationic complex and anionic complex. While naming cationic complex, there is no special ending. But in the anionic complex, name of the metal atom or ion ends with ATE. Then, while writing the name of the complex compound, oxidation number, it is written after the name of the central metal atom or metal ion in a simple bracket. So these are some rules to be followed while writing the IUPAC name of complex compound. Now, we'll go for the First one, K4 Fe CN6. This is cation. So potassium. This is the complex ion. Here first preference is given for ligand. There are 6 ligands. Hexa, cyanido. And it is a negative complex. Name of the central metal atom ends with A8. Ferrate. Now, oxidation state is 2. Say. Potassium hexacyanido ferrate 2. One more complex compound, cuprammonium sulfate, Cu, NH3 4 times, SO4. Now, complex ion is a cation. First preference is given for cation. Now, this is a complex ion, coordination sphere. Now, while naming, first preference given for ligand, tetra. Amine, 2 tetramine, double M. If you write single M, that refers to NH2. Tetramine, copper. Oxidation state is 2, copper 2. Simple ion, sulfate. Simple ion is sulfate. One more example. Here oxidation state of cobalt is plus 3. Because ethylene diamine is neutral 0. This is a minus 3. If it should be plus 3. Where ethylene diamine is an example for complex ligand, ethylene diamine, there is one prefix. So here, special kind of prefix is taken, tris. 1,2. Ethane diamine. 1,2. Ethane diamine. Cobalt. This part is positive, therefore cobalt. What is the oxidation rate of cobalt? 3. Cobalt 3. Chloride. And no capital letters are used, only small letters, and it is a single sentence. Continuous, no space is left vacant between the name of the ligands. Okay. So these are some example for Iupac nomenclature of coordination compound. Next we'll move on to isomerism. So coordination compound exhibit structural isomerism as well as stereoisomerism. Now, example for structural isomerism and structural isomerism. First one about ionization isomerism. Here isomers differ in the formation of ions. That kind of isomers are called as ionization isomerism. For example, there are isomers. They differ in simple ion. It contains bromide ion. It contains chloride ion. Therefore, it is an example for ionization isomerism. Next one about the linkage isomerism. Linkage isomerism. Linkage isomerism is observed when coordination compound which contains ambidentate ligands. And these isomers differ in the ligating atom. That kind of isomer is called as linkage isomerism. They should be ambidentate ligand and they differ in ligating atom. Okay. Now, for example, cobalt complex CO, NO2, NH3, 5 times Cl2. Another complex cobalt, ONO, NH3, 5 times Cl2. Now here nitro group and the nitrite. NO2 group, N-hydroxyl ligand, nitrogen is the donor atom. ONO, where oxygen is the donor atom. Now, next about hydrate isomerism or solvate. Hydrate isomerism. Here isomers differ in the number of water molecule acting as a ligand. For example, it's a chromium complex, Cl3, the Cl2, H2O, Cr, H2 4 times, Cl2, Cl dot 2H2. So these are isomers, but they differ in number of water molecule. Here acting as a ligand 6 water molecule, 5 water molecule, 4 water molecule. This kind of isomerism is called as hydrate isomerism. Next about coordination isomerism. In coordination isomerism, ligands can be interchanged. Coordination isomerism. Coordination isomerism. Ligands can be interchanged. Now, so example for coordination isomerism. Example for coordination isomerism. CO NH3 6 times. Cr F6. Now, in this complex, you can write like this, another isomer, Cr NH3 6 CO F6. Cobalt is plus, so here plus 3. Here chromium is plus 3, minus 6, it is a minus, so plus 3 minus 3, 0. Same here also, say chromium plus 3, 0, this plus 3. Here cobalt is plus 3, F6 minus 6, so charge on this part is minus 3. So here the ligands can be interchanged. That kind of complex is called as coordination isomerism. Next, moving on to stereoisomerism. Stereoisomerism. In stereoisomerism, coordination compound exhibit cis and trans, as well as it also exhibit optical isomerism. It also exhibit optical isomerism. Now, say about the stereoisomerism. In this first one about geometrical isomerism. Geometrical isomerism. Whenever you guess the type of isomerism, first thing you should learn based on the general formula of the complex. General formula of the complex. Now, about the stereoisomerism. Stereoisomerism. First about cis and trans. Cis and trans. Just look here. That is in the case of geometrical isomerism. Coordination compounds with coordination number 4. Coordination number 4. Here, tetrahedral complex, they fails to exhibit cis and trans. Square planar complex, they exhibit cis and trans isomerism. Now, in the case of square planar complex, general formula, M central atom, A2, X2. Here A refers to unidentate, X refers to unidentate but negative. Okay. M, A2, X2. Now, next one is M, A2, XY. Okay. One more formula, M, AB, X2. Okay. Or M, AB, XY, AB, X. All these are square planar complex. They exhibit cis and trans isomerism. I'll take this example. Now, central atom is written as M. Okay. A2, XY, Okay. A2, XY. X, Y. Here, when ligands are present closer, that kind of isomerism is called cis isomer. Cis. Or if it is represented like this, here ligand is far from each other, that's called as trans isomer. That forms a trans isomer. Similarly, you can write the isomer for all these complex compounds. Now, if you take this one, MABXY, there are 4 different ligands. By fixing the position of one ligand, you can write 3 isomers. So, this kind of formula for the complex compound that exhibit 3 isomers, where position of one ligand is fixed, and by changing the position of other ligand, we can write 3 isomers. Now, next, we will move on to coordination number 6. When the complex compound, it exhibits the coordination number 6. It also exhibits cis and trans isomerism. Some of the formula MX4A2. Okay. Or we can write one more, MA3X3. So this is general formula for the complex compound where it exhibit different types of isomers, cis and trans. Now, one more example we can write like this, MA4 X and Y. Here we can write like this because unidentical ligand A4 A4X2. Now, in the case of MA3X3, there is special type of isomerism that's called as facial isomerism and meridional isomerism. Okay, I'll go for this complex MA3X3. Where cis form is called as facial, trans form is called as meridional. There are 6 ligands. Geometry is octahedral. And all these complex with this formula, they exhibit octahedral geometry. I'll write X. This is X. When you consider these 3 ligands, this is present at the one face of the octahedron. Therefore, this is called as facial or cis isomerism. Or if I write like this, 6 coordinate bond, X and X. Ligand A and A. When you consider these X ligands, say, this leads to meridional isomerism. Meridional means that is trans isomer. Here these are closer. Okay. So cis isomer is facial and trans isomer is meridional. It is observed in the case of the complex having formula MA3X3. Next, about the optical isomerism. In optical isomerism, the mirror image of the isomers, they are non-superimposable. Therefore, they exhibit optical isomerism and they differ in the direction of rotation of plane of polarized light. Now, about the optical isomerism. Now, of the type MAA thrice 2 ligand, that means it is a bidentate ligand. Now, we can go for one example. Tris, ethylene diamine with +3 charge. Central metal ion is cobalt. There are three ligands, that is ethylene diamine. If you arrange the ligand ethylene diamine in this way, the mirror image of this isomer is non-superimposable. Ethylene diamine, ethylene diamine, ethylene diamine. Say. Charge on this complex ion is +3. But the mirror image is non-superimposable. Therefore, it is an example for optical isomerism. So, one more. With formula MAA2 and X2. Example for this formula, CO, ethylene diamine twice Cl2 plus. So this compound also exhibits optical isomerism. Now, next we'll move on to VBT, valence bond theory. Okay. So according to this theory, in a complex compound, central metal atom or metal ion possess vacant d orbital, and vacant d orbital is available for hybridization. Number of hybrid orbitals formed is equals to number of orbitals involved in the process, and geometry of the complex that depends on the type of hybridization. sp3 tetrahedral, dsp2 square planar, d2sp3 or sp3d2, that leads to octahedral complex. Then, about the magnetic property. If there is unpaired electron, that exhibit paramagnetic. If there is no unpaired electron, that exhibit diamagnetic property. And all the information is given in this theory. Now, we'll take one example. Okay. And also about the inner complex and the outer complex. Now, so what about the inner complex? If n-1 d orbitals are involved, that's called as inner complex. Only nd orbitals are involved, that kind of complex is called as outer complex. Then again, based on the strength of the ligand, there is low spin complex and the high spin complex. If the strong ligands are present in the complex compound, that leads to give low spin complex. That's called a low spin, inner complex. Only weak ligands are present in the coordination compound, that's called as high spin, and that results in the outer complex. Now, we'll take some examples. Now, with the nickel ion, Ni+2. Now, so electronic configuration of nickel +2, argon, 4s0, 3d8. D electrons are arranged like this. D electrons. There are 8 electrons. Now, nickel +2, there are 2 unpaired electrons, and magnetic property is paramagnetic. Now, when nickel +2 combines with ligand, first we'll go for the weak ligand, NiCl4. 2 minus. Chloridoligand is a weak ligand. Now, in presence of chloridoligand, electronic configuration of nickel. Now, 8 electrons are arranged like this. Since ligands are weaker, there is no spin pairing. Now, therefore, this undergo sp3 hybridization. Which kind of hybridization? sp3 hybridization. Hybrid orbitals are occupied by the electrons donated by the ligand. There are 4 chloridoligand, 8 electrons. donated by the ligand. This is about electronic configuration of this complex ion. Now look at this. There are two unpaired electrons. So what about the magnetic property? Paramagnetic. In most of the cases, when central metal atom or metal ion is bonded with weak ligand, the magnetic behavior is paramagnetic. Now, we'll take another complex with strong ligand, Ni, Cn, 4 times, 2 minus. Here cyanide is a strong ligand. So spin pairing takes place, Now, arrangement of electrons, Look here. This is nickel plus 2. In presence of strong ligand, those unpaired electrons are forced to pair up. There are 4 cyanide ligands. So it requires 4 hybrid orbitals, 1d, 1s, 2p. So d, s, p2 hybridization. And it is occupied by the electrons donated by the ligand. So in the electronic configuration of this complex ion, there is no unpaired electron. Therefore, it exhibits diamagnetic property. Here we have taken nickel ion. We'll go for one more example because this is the most important part for most of the competitive exam. They'll go for paramagnetic or electronic configuration, or say this is inner complex. Only inner orbitals are involved. Inner orbital n-1 d orbitals involved. Now, one more example with manganese. Mn plus 2. In Mn plus 2, there are 5 unpaired electrons in d orbital. Okay. So this exhibits paramagnetic property. When Mn plus 2 combines with cyanide ligand Mn, Cn6, this is plus 2, minus 6, charge is minus 4. And it is a strong ligand. So there is spin pairing takes place. These 5 electrons are arranged like this, correct? Arranged like this. Still it contains one unpaired electron. Now, there are 6 ligands, so this undergo D2sp3 hybridization. Octahedral geometry. And there is one unpaired electron, therefore it exhibits paramagnetic character. Like this, based on the VBT, we can explain different types of complex compounds or complex ions. Now, the next part is about spectrochemical series. Now, it is a series which indicates strength of the ligand. That series is called as spectrochemical series, like weak field ligand and strong field ligand. CO, carbon monoxide, is the strongest ligand. Spectrochemical series. From weak field ligand to strong field ligand, say I minus, Br minus, SCN minus, thiocyanide, Cl minus, S minus 2. All these are weak field ligand. F minus, OH minus, C2 oxalato, C2O4 2 minus, H2O. After H2O, NCS minus, EDTA. After EDTA, ammonia, NH3. After ammonia, ethylene diamine. Then after ethylene diamine, NO2 minus, then Cn minus, then CO. Usually after water, this is weak field ligand, this side. This is strong field ligand, Now from here if you go, strength of the ligand increases, So these are weak field ligand. These are strong field ligand. When weak field ligand combines with the central metal atom or metal ion, there is no spin pairing and most of the complexes are paramagnetic. Strong field ligand, when it combines with central metal atom or metal ion, there is spin pairing, and that depends on how the electronic configuration takes place in the complex. It exhibits diamagnetic or paramagnetic character. Now, so after spectrochemical series, next we will move on to crystal field splitting. Crystal field splitting. Say. So what about crystal field splitting? When transition metal ion combines with ligand, it loses its energy and reaches higher energy state, unstable state. From the higher energy state, they split into two types of energy level, that is T2G and EG. T2G and EG. If there are 6 ligands, that kind of splitting is called as octahedral splitting. If there are 4 ligands, that's called as tetrahedral splitting. Tetrahedral splitting. Now, first we will move on to about the octahedral splitting. Crystal field theory. Crystal field theory. Okay. Octahedral splitting. Transition metal ion in its ordinary state, energy lower. No. When it combines with ligand, its energy increases. Energy increases. Okay. D orbital energy increases. Now, so here the average energy of d orbital, in presence of spherical crystal field. No. Energy is more, stability is less. So it's split up into two types of energy level, that is T2G and EG. T2G and EG. This is EG, this is T2G. Now energy separation, that's called as crystal field stabilization energy, or it is written as delta O, or refers to octahedral splitting. When electron enters into the T2G orbital, energy decreases. When electron enters into the EG orbital, energy is raised. Now, look here. So here, when electron enters into T2G, energy is decreased by 0.4. When electron enters into the EG, energy is increased by 0.6. Where delta O, that refers to octahedral splitting. Now, so in order to calculate total energy. So this is equals to, see, here this is 3 into minus 0.4 delta O plus 2 into 0.6 delta O. So this is equals to minus 1.2, this is plus 1.2 delta O. Now, equals to 0. That is about total energy in the T2G level and the EG level when the electron go or and it's completely failed. Now, so this is about the octahedral splitting. Now, how to calculate crystal field stabilization energy? Crystal field stabilization energy. Now, crystal field stabilization energy, that is equals to x into 0.4 plus y into 0.6 delta O. X and y, that refers to the electrons present in T2G level and EG level. T2G level and EG level. Now, so this is about the crystal field splitting. Now, oxidation state is directly proportional to crystal field splitting. oxidation state of central metal atom or metal ion is directly proportional to crystal field splitting. When you go for tetrahedral splitting, it is the reverse. Eg has got lower energy, T2G has got higher energy. When you compare tetrahedral splitting, delta T, that is equals to 4 by 9 delta O. Okay. So this is about crystal field stabilization energy. Now, quickly moving on to stability of coordination compound. Stability of coordination compound, that depends on the charge on the central metal ion. Greater the charge, greater is stability. For example, ferro and ferri. Complex compound with the ferric ion, that is more stable. Similarly, it also depends on the nature of the ligand. If the strength of the ligand is more, that's the more stable is the compound. Chelating ligands, if per ligand number of coordinate bond formed is more, such complex compound is more stable. For example, if central metal atom or metal ion is bonded with one hexadentate ligand, that forms at a time 6 coordinate bond. Central metal atom or metal ion is bonded with 6 monodentate ligand. In that, the first one is more stable. Where central metal atom or metal ion is bonded with one hexadentate ligand. And it also depends on the stability, also depends on the charge density of the central metal atom or metal ion. And also, if the basic nature of the ligand is more, greater is the stability of the complex compound. Last, about the magnetic property and color of coordination compound. So, coordination compounds are made up of transition metals. In transition metal, color that depends on the unpaired electron and DD transition. Same in the complex compound. Transition series, the first transition series, they are in visible region. So, when white light falls on the aqueous solution of complex compound, it absorbs definite frequency. Rest of the frequency is emitted out. That is the complementary color. So, complementary color, that gives the color of the complex compound. About the magnetic property, it can be calculated using the formula mu is equals to root of n into n plus 2. Unit is Bohr magneton. N refers to number of unpaired electron. If complex compound, after writing the electronic configuration, if there is one unpaired electron, then you can calculate the magnetic moment. Or based on the presence of unpaired electron, we can decide the magnetic property. If there is unpaired electron, such complex compound exhibit paramagnetic. If there is no unpaired electron, they exhibit diamagnetic property. Okay. So, this is about the complex compounds or coordination compounds.